Okay, for what we have in this case of operations between matrices, we are given three matrices. Okay, the first we have A, which is going to be a 2 by 3 matrix where we have the top row consisting of 1, 2, 3, the bottom row with the numbers 4, 3, 2. And we have matrix B, which is also a 2 by 3 matrix where we have the top row to consist of -1, -2, 3, and the bottom row consisting of -4, 3, and -2. And for C, okay, this is what is regarded as a 3 by 1 matrix, since we have 3 rows and only 1 column. And we have consisting of the elements 5, 6, and 7. And it says to determine the following among the matrix operations if possible. And for what we have in the first case, now we're looking at taking the addition of A and B. So we're looking at adding these two matrices, and if we look at the corresponding elements, okay, see we have for the top row sections, okay, we have A, 1, 2, 3, B with -1, -2, and 3, and if we combine the respective parts, we have 1 plus -1, 2 plus -2, 3 plus 3, and applying the same kind of treatment, okay, to the bottom row, we have 4 combined with -4, 3 with 3, and 2 and -2, and we have for the outcome, okay, we have the sum to end up with the top row with 0, 0, 6, and the bottom row with 0, 6, and 0. Now for what we have in the case of taking the difference, whereupon we have B minus A, and if we look at taking the difference, okay, B minus A, so I'm taking 1, 2, 3, 4, 3, 2 away from -1, -2, 3, -4, 3, -2, and so just looking at subtracting the corresponding parts, so I have like -1 minus 1, -2 minus 2, 3 minus 3, and for the bottom row I have -4 minus 4, 3 minus 3, -2 minus 2, and we come out to the resulting difference at -2, -4, 0 for the top row, and -8, 0, 4, -4 for the bottom. And trying to add the matrices A and C together. Again, A is a 2 by 3 matrix and C is a 3 by 1 matrix, and since the dimensions do not match up, now we could add and subtract what we have between matrices A and B, since both of those are 2 by 3 arrangements. But in the case of C, okay, trying to match up with A, there's a mismatch, and so there is no solution. Okay, so for what we have for A times B, okay, to be able to multiply matrices, the number of columns in the first matrix must match up with the number of rows in the second matrix. Okay, and if you notice, okay, we have number of columns in matrix A is going to be 3, number of rows in the second matrix B is 2, and 3 and 2 are not equal to each other, so we need not follow through with multiplying, because here we have a dimensional mismatch in this capacity, and so there is no solution. So while we can add and subtract activity immediately between matrices A and B, you cannot multiply these matrices together. Now, looking at what we have for the next attempts at multiplying matrices, and we have A times C, and A again is a 2 by 3 matrix, and C is going to be a 3 by 1 matrix. And guess what? Number of columns from A is equal to the number of rows from C, and for what I have for the outside numbers M and P, okay, we're going to have, in this case, once I take the product of M and P, this will take or be in the form of 2 by 1, and that will be the dimensions for the matrix product which we will have with AC. So just looking at what we have multiplying, so have 1, 2, 3, 4, 3, 2 multiplied by 5, 6, and 7. And what I'm going to do here in terms of the correspondence, in terms of going about multiplying, so again with the top row from A and 5, 6, 7 from C, I'm going to multiply the corresponding parts here. We have like the first elements row by row from A will be matched up with the column elements C. So I have 1 is going to be matched with 5, 2 with 6, 3 with 7, and those products will be added together, and then working with the second row in A and mapping with again 5, 6, 7. So you have 4, 5, 3, 6, 2, and 7, and taking the products and combining, and it's going to result that for AC, again, you have a 2x1 matrix, and the outcome we have with the top number at 38 and the bottom with 52. And we have taking the product of B and C. Now we got another 2x3 and 3x1 matrix, and the size of BC, just like AC, is going to be 2x1, and applying the same treatment. Okay, so again, have the top row from B match with the respective products. They have -1 mat with 5, -2 with 6, 3 with 7, and for the second row from B mat with the respective elements from C, we have -4 mat with 5, 3 with 6, -2 with 7, adding the products throughout. And for the 2x1 matrix, for what we have with B times C, this comes out to where we have the top number at 4 and the bottom number at -16. And for what we have in the case of C times A, again, C is a 3x1 matrix and A is a 2x3 matrix. And notice that we can multiply together A and C, but switching the order with C at the front, guess what? We had the number of columns, okay, to be at 1, and for the number of rows with A to follow, we have 2, and guess what? 1 does not equal to 2. So while there is a solution for A times C, there is none for C times A. And looking at scalar multiples, if I'm looking at 3 times matrix B and deducting twice matrix A, so just taking what are referred to as scalar multiples. Okay, so I'm looking at 3 times matrix B, and I'm taking twice matrix A, and taking the difference between the respective products. Okay, and so for what we have in this case, we still have a difference between 2x3 matrices, and the difference is also going to be a 2x3 matrix. And for the result, we have the top numbers at -5, -10, and 3, and the bottom we have -23 and -10.